there's something in your homework I should probably mention. I believe, didn't I do an energy loss during impact? Did I comment on that the other day or not?
You mentioned that one exists.
Okay, I mentioned that there is energy loss. So what's going to happen in your problem, and I'm just covering up my little comments I wrote on this homework question you have here, is you've got a bullet that's traveling at 2,000 feet per second. Pretty fast. So that bullet comes in here and it hits into this box of 50 pounds of sand. And the bullet only weighs 2 ounces. 16 ounces in a pound, so 1/8 of a pound. Pretty big bullet. So that thing comes in, hits into this thing, and then embeds itself in there, and then it gives this 50 pounds plus the 2 ounces some momentum. When that transition occurs, there is an interaction of forces between, with my fingertips I'll show you. When these things come in contact, there is a force of interaction, the bullet against the block and the block acting against the bullet over a very short duration of time. So they are equal and opposing impulses. That makes sense? Equal and opposing impulses during the impact. So there's no net impulse. There's no net impulse occurring. What happens whenever that occurs is there is a loss of energy in the system. And you can compute that loss of energy to answer that second part of the question here. You can compute that loss of energy right during the impact because you know the kinetic energy in this system just before impact. The pendulum was just hanging there, the 50 pounds of sand. That bullet's carrying some fairly significant kinetic energy. Okay? Fairly significant kinetic energy. After the bullet's embedded itself in here, now the combined mass has a velocity. It's now carrying some kinetic energy. So what's that change in kinetic energy? That's the energy loss that's occurred. The change in kinetic energy during the impact, from before the impact to just after the impact, is the energy loss. So it's an easy calculation to do, and it'll show you that indeed there's a fairly considerable energy loss there. That always occurs. Same thing will happen in another question on the next page here, shown here. We let this body come down here. It picks up speed, just like on your exam question. Picks up speed. And how could you easily figure out the speed of that slide? Yeah, it's just a loss of potential energy. Giving up potential energy gives it the kinetic energy it has when it comes in and hits into this, and then right once it embeds itself, it's now on a friction surface and starts to slide. If I get time in another day or two, I might come back and do this problem with you, because there's several problems several things you can do here. One is you can use work energy to figure out the speed it happens to have just before it goes in here. Then you use impulse momentum to get the change in momentum, to get the combined speed of this right here. Then it's now on this friction surface, and you go back and use work energy to figure out the distance that it slides before it stops. Did you hear all that? I'll abbreviate it one more time. Work energy to figure out the speed of this thing as it slides down here. It's just a loss of gravitational potential. Gives it the kinetic energy. Then it impacts this block through impulse momentum. You get the speed here. Then you go back to work energy and work the problem now with a combined mass right here with its velocity. And then you let it slide under the action of the resisting friction force until it comes to rest. Okay. Nice little 3-step.
Would you even need impulse momentum in that one, because if you have that block A sliding down with a certain amount of joules, there's that much energy in the system, it hits the other block, and now it's the same amount of energy, it's just moving more mass, so we can figure out what the velocity would be.
There's an energy loss during that impact.
Oh well.
Okay, there's always going to be energy loss during impact. So that's what you wouldn't have accounted for. Okay, we have about 20 minutes left. Let's go over to angular impulse momentum and make sure that we get a bit of a handle on working a problem or two with that. First of all, I want to just show you this, which is what I went over with you in the last class session, is I developed for you the impulse momentum concept, and here's the defined value of angular momentum. Lever arm crossed with momentum. Lever arm crossed with momentum. Then here's a determinant, and whichever way you wish to carry out that determinant, you can do it. You saw the way that I do it. And then you get these three vector components of that angular momentum. Now, I want to go up here on the board and show you the approach that they took to come up with the concept compared to what I did with you last class session. Just to refresh your memory, I started with moment equals R cross F, which was R crossed with M dV dt, and then we kicked the dt over and ended up with the concept. The angular impulse, which is moment or torque acting over time, imparts a change in angular momentum. Okay, that's the way I approached it. And we ended up with the angular momentum state 2 minus the angular momentum state 1 is equal to this angular impulse. The approach the book uses is they start with a definition of angular momentum as being R cross mv. Now, if we take the time derivative of this, we get, when you differentiate position vector, what do you get? I'm differentiating a cross product.
It's like the product rule.
You use the product rule just like you did in first term calculus. Okay, so the derivative of R with respect, the R position vector with respect to time is what? Well, not.
Oh, the whole thing?
No, just this. Derivative of R with respect to t is velocity, isn't it? Crossed with leave the other function alone, plus R crossed with m dv dt. And so what we get is that the time derivative of the angular momentum is equal to, this is what? dr dt. 4 weeks ago, that's velocity vector. Okay, that's your velocity vector. Now what happens when you cross a vector with a vector in the same direction? Cross product. If you have two vectors in the same direction, you cross one into the other, you know that they're equal to, the magnitude of it's equal to the product of the magnitudes times the sine of the angle between them. If the angle is 0 between them, then the cross product of V crossed MV is 0. So that term zeroes out, and you're just left with R cross MA, which is R cross F. Sorry, I'm running out of steam here with my markers. R cross F, which is equal to the moment applied. So the rate of change of angular momentum is equal to the moment applied. Then if you would take this thing and integrate it, you'll end up with the concept I ended up with over here. Okay, so their discussion began with this as a defined quantity, and then they cranked the derivative on it. So you'll oftentimes see this angular momentum concept in more advanced dynamics presented to you in this fashion. Okay, I think we have time to do a quick problem. Here's one, number 241. So if I can bring that in a little more. Two-tenths of a kilogram ball, supporting cord, revolving about a vertical axis on a smooth conical surface with an angular velocity of 4 radians per second. So it's swinging around, coming towards us and around on this conical surface. The ball's held in position with B equal to 300 millimeters by a tension of T in the cord. If the distance is reduced to the constant value of 200 millimeters by increasing the tension in the cord, compute the new angular velocity and then the work done in the system by T. Two kilogram mass on a 30-degree conical surface. Two-tenths of a kilogram. Normal force, tension in cord, distance B. This thing comes over, okay. And B was initially 300 millimeters,
Yes.
right? So I'm going to write that as 0.3. So B initial is 0.3 meters. And then, did they give us a B final?
Reduced to 200.
Okay. So B final is 0.2 meters. Okay. And the question being asked was?
Compute the new angular velocity.
Okay. So, and we have, this thing's coming towards us. So it's following what kind of path? Circular path. Circular path. Okay. Initially. Then we're going to pull this cord. We're going to pull this cord and cause this block to slide up this frictionless surface a little bit, so that now it's only 0.2 of a meter from the top, and it's going to have some different, it's on still a circular path then, but it's on a smaller circular path. Okay. So if we look, this is an elevation view. if we look at a plan view of this, initial, then we'd look down on this and we'd see this circular path. Plan view final is going to be a smaller radius path. Okay. The object's out here. I'm looking down on it. So it's out here, and what's this radius?
It's going to be 300 or 0.3.
With some signs.
Oh, I see. 0.3.
Yeah. This incline was 30 degrees, wasn't it? So B, so we have B, this is the effective radius right here. Is right here, this distance. So that's going to be equal to B cosine of 30 degrees. Or the initial radius is going to be then 0.3 square root of 3 over 2. And the final radius is going to be 0.2 meters cosine of 30, 0.2 square root of 3 over 2. Or 0.15 square root of 3. And over here, 0.1 square root of 3. The object is moving this way in this plan view, looking down from the top. So its speed is what?
So omega.
Did they give us an initial omega?
4 radians per second.
So the omega initial was 4 radians per second, and you know, here's your R initial, you know that the speed is R omega. So we have this momentum being carried, and the mass was what?
0.2 kilograms.
0.2 kilograms. So we have the momentum here, mv initial is going to be equal to 0.2 kilograms times R, which is 0.15 square root of 3 times the omega of 4. So this is the momentum. What's its angular momentum? What is angular momentum? R cross mv. What's the angle between these two? 90 degrees. So the sine of 90 degrees is 1. So it's real easy when you're in circular motion. Angular momentum is easy as long as you think about it. And keep in mind the goodies that make it up. Okay? It's got the lever arm and it's got the momentum. And so the angular momentum initial then is going to be equal to, and it's out of the board, isn't it? Coming towards us. The angular momentum is coming out towards us, and it's going to be a value made up of R, which we know here, times the mv, which is here. So it's going to be the product of these two items that I have my finger on. So you can see that it's going to be 0.2. It's going to have 0.15 squared, isn't it? It's going to have square root of 3 times square root of 3, which is a 3, and it's going to have the 4 in it. What are the units? What are the units of this crazy thing? It's going to be length, which in this case is meters, And we have mass, which is kilograms, and we have meters per second. Kilogram meters squared per second. Except we don't call it that. What's the other side of the equation? Instead of thinking of these screwy units, what's the other side of the equation where you have a delta of this? It's moment acting over time, isn't it? Newton meter seconds. And a Newton is a kilogram meter per second squared. So if you're getting something screwy out of these units, then think of the other side of the equation and it'll give it to you. Okay, so here's the initial angular momentum carried by it. Then what about the final?
Going to be the final radius multiplied by some new omega.
Okay, and they asked us for the omega, didn't they? See, so the particle is now at some different omega right here. And so to make a long story short, the final must be equal to R cross MV, which is our R is this value right here. And what's our momentum now? 0.2, same mass, MV. Yeah. 0.1 square root of 3 times the new omega, which we don't know, right? Okay, so there it is. So we're multiplying this thing by this, and so what we get is 0.2, 0.1 squared, 3 from the square of the square roots, over 2, no, I took care of that, times the omega. Is there any torque? No torque. So this change here, this change in angular momentum is equal to 0. You know what this is called? Conservation of angular momentum. That's what's going on in this problem. So we set this scalar value equal to that scalar value, just divide by those terms, and you get the final omega, and the answer to that is 9 radians per second. 9 radians per second. You can check that calculation, and we're out of time today. There's another class due in here in a couple minutes. Okay, so I barely got through that one.